Okay, thank you very much for the invitation and the opportunity to be here. Okay, so this is our title. So first we will give the definition of pseudo-rotation. So first of all, the annulus is this, write it this way, and pseudo-rotation is a homeomorphism of the annulus. Okay, so a pseudo-rotation is a homeomorphism of the annulus without periodic points. Without periodic points. So this is the definition of the pseudo-rotation. We will denote this just by p rotation. Okay. So first of all, we define this. So for each pseudo-rotation, so each pseudo-rotation f admits a unique rotation number denoted by rho f is something in this. But actually, it is is always irrational. So is that defined as the limit of this, say, P1 f and xy. So here f is a lift of this small f, minuscule f, to the universal cover of annulus. The universal cover of annulus is this. And the P1 is just a projection to the first coordinates. It's the P1. So it's the speed of the rotate along the first coordinate. So for each irrational alpha, we set this f infinite a alpha. So we define it as the set of pseudo-rotations, which is the infinite diffeomorphism, and also you assume it's error preserving with a rotation number alpha. So it's the set of error preserving infinite diffeomorphism with a rotation number alpha. We denote it by this. So we denote this, define as O AX alpha. This is a more special collection of a pseudo-rotation, which is just this. So as those pseudo-rotations that are conjugate to the rigid rotation. So the main result of ours is the joint work with Barney Brenham is the following. So bigger, okay. Okay, sorry. So there, generic alpha this set is the C-infinite closure of that set. So this is our first, like our main result. So we first introduce a corollary. The corollary is the following. So the corollary is that still for this bare generic alpha, so for generic alpha weakly mixing pseudo-rotation, and we make a bit remark. So is just that first remark is that you cannot remove this generic condition to every alpha, because if you have for Differentiable alpha, there's a Kn result of Hermann, Fayad, Kokorian. So they show that if you have this pseudo-rotation with a differential rotation number, which are close in the C-infinite topology to the rigid rotation, then it is C-infinitely conjugate to the rigid rotation. In particular, you cannot be weakly mixing. Also, you know that you cannot improve this, or for generic alpha, this set contains no mixing, if you for this generic alpha. This is not that new. It's not in our theorem, but it is a corollary of a paper of Abdullah Fayyad, Calvey, Yishen Xu, and me. We show this non-mixing result for pseudo-rotation on disk, but the proof can be adapted to show that as well. The example is known due to the method of Annulus and Katok. So basically, Annulus and Katok, they already showed this result for this set in place of that set. So inside of this set for generic alpha, you know that the C-infinite, you know that the weakly mixing pseudo-rotation are C-infinite generic. So we just established this link.
Is there any explicit example?
There are. Like, depending on what you mean by explicit, the construction is inductive, and in the limit you get. Okay, so.
The closure, if you close the set, do you get if you have the periodic point, or how do you have the...
No, you don't have the periodic point.
Okay, so even taking the closure.
Yes. That is not new. Like the main, basically we need to do this. For the other inclusion is already known before. Sort of follows from so-called Frank's lemma. And okay, so maybe I should provide some motivation for this result. So first, the motivation. So first, the motivation is that for circle diffeos, there's a theory developed by Hermann and Yokos. So basically, they consider this. These are C-infinity homomorphisms of the alpha with rotation alpha on the circle, and this equals to this alpha equals to this. This is if alpha is a Differentiable. When this is not Differentiable, you still have this, but in this place you have a so these two things are not equal. This is a Liouville number. So this is Hermann-Yokos result. So I should comment a little bit about this. So this result is first, I guess, since related to this is first studied by anode, basically followed by certain homograph. And then anode consider this problem for C omega, and then generalized to C infinite category by Moser. And but all of these results are perturbative. Then Hermann did it for almost every alpha. So in the end, it is done by your course for every this Differentiable alpha. So, but then in like slow regularity, there's also a result of Cauchy-Nielsen and Austin, which give you the sharp regularity. So for Liouville, this is the first conjectured by Hermann, and in this case, he already proved that this inequality holds for generic alpha. The proof is very short, and then it is completely solved by your course for every Liouville number. So although the proof in this part, so our result is similar to result of Hermann in this part, because he also did a not generic set of rotation number. But I'm trying to say that the method cannot be adapted directly to that side. Basically, Hermann needs to study the variation of a rotation number. Object like this. For circle differentialism, of course, you can always define this, but for annulus, it is not defined. And also, even if you have this, you need this the first part to do that. So this is like one motivation, and the other motivation is this result of is this a question of a Katok? Katok's question. So Katok asks that. So this is still widely open. Yes, that if every low-dimensional system with topological entropy 0, a limit of integrable systems. So he didn't make this question very precise, but the first satisfactory answer is provided by my cause, Barney Bram. So is the Bram's result. It shows that so every C infinite omega preserving pseudo-rotation on disk a limit of periodic. This is a C infinite limit of a periodic difference. So basically, the statement is more precise than that. Also C infinite. So you have F, then you find the sequence of G and converge to F in C0. Any of this, each of these differentiable is C infinite error preserving. Also, they have this property. Okay. Yes. A pseudo-rotation on the disk means that they have the one perfect point, the minimum number. Okay. So this is Bram's result, and it is a general. It is like slightly. There's a variation done by Le Cavalier, but he needs to assume. So in Le Cavalier's result is still C0 approximation, but he can weaken this regularity to C1. But he needs to assume that the restriction of the differentialism on the boundary is a linearizable. So it is also quite strong. But then Barney used his result. It's still a Bram's result. It shows that so for this still a pseudo-rotation F with this rotation number very Liouville. Is rigid. C0 rigid means that there's a sequence Nj. So they converge to the identity in C0 topology. So this is Brenham's result, and then so we these 5 people. So we generalized Brenham's results to C infinite convergence. We proved this. So what we did is basically to try to generalize this. So motivation for us at the beginning is to try to generalize these results. Okay, so maybe I should talk a bit. Okay, I will mention this now. Okay, so the shorter answer is that we know the existence of generic sets, but somehow in the proof there's like most of the steps are very explicit, but there's one step we just get certain bound by certain compactness arguments. So I don't know any bound, and Barney at some point told me that he has some bound, but the bound he gets is written in terms of the generator of the Hamiltonian, so it's not quite that like it's a bit different proof. So the idea of the proof is somewhat straightforward. So basically, the starting point is still a lemma of the following type. So this is a lemma in this paper, but it has its roots in work of Franks and Handel. So basically, if you have a map, a pseudo-rotation on disk, or like annulus is the same, you know that if it's ever preserving with rotation number alpha. So let's say alpha is between 0 and 1. Then if this D is a topological disk with this area bigger than so in this case we assume this is not a homeomorphism but a diffeomorphism, C1 pseudo-rotation. If this is bigger than some constant times alpha square root of alpha times the Lipschitz constant of f, then fd intersect d non-trivially. So so having this result, I mean, this is proved just by Kake's lemma combined with Frank's lemma. Having this, we know the following thing. We can majorize the C0 displacement of a pseudo-rotation in terms of the, okay, in terms of the, sorry. This is just alpha. Sorry, here is alpha square, and here is alpha so plus 1. So we have this bound. So basically, if you take any point, you draw a circle around it. If the displacement is too long, and also the Lipschitz constant is not very big, it cannot intersect itself because you're assuming the displacement is too big. So having this, we can get the following non-trivial estimate in terms of the higher derivative of f. Because we have this convexity equality. This is the we have this. So once if you know the derivative of this is not too big, and the rotation number is somehow very, very small, then you have a non-trivial estimate of this derivative. So having this in mind, basically we consider f, consider iterate of f, then this rotation number could be much, much smaller if you impose some very strong arithmetic condition. then you use this to measurize this, so you get that. But how do you use it to construct the approximation? So it is done in several steps. Okay, the main idea is the following. If you want to do a periodic approximation of the circle, one way is to use this Rocklin tower. For example, if you have, let's write this as 0, and so for simplicity, let us write n instead of n alpha. Okay, then you can consider this thing. You can decompose the circle into the following disjoint union of smaller of intervals like this. So maybe I should write this f and f and t. So say now I'm assuming that f is a circle diffeomorphism, and then at this point you have 2n minus 1 is qn plus 1 minus 1. This is this. This is qn. This is qn to qn. All the way to some point you have qn plus 1 minus 1, and here qn plus 1 plus qn minus 1, qn plus 1 plus qn minus 2. This is a qn plus 1 minus 2. Okay, so you can decompose this circle into unions of these intervals. For instance, you can just find so basically this is like a very useful. We'll see later why it is useful. But imagine that you can do the same thing for annulus. So basically, you have this annulus written like this. You can cut it. You can find some curve, right? And use some other curve. Basically, FQN. Right? Another curve. So that is so. This is not. Let's say. I use another color. These two things can intersect. This is FQN plus 1 gamma. So let's say if you can find a curve so that a curve gamma, so that FQN gamma and FQN plus QN plus 1 minus 1 alpha, all of these curves are mutually disjoint. So let us assume for now that we can do this. They are mutually disjoint. Then we can cut the annulus like in a similar way. So notice that this white curve and the green curve does not have to be disjoint. Okay. Because I mean, it's like so they do not need to disjoint. So this does not contradict that the disjointness of these curves. Because if you just ship it back, then it will be qn plus 1 that. But maybe you have a disjoint. You have an intersection for these two. So imagine that you can do this, and also let us imagine that we can also somehow get the geometric control of this region. So one region is white and white. Another region is green and white. Let's say this is D0, this is D. So imagine that I have a H that maps D to D0, so that on the boundary, what happens on boundary? So I require two conditions. The first condition is that H is identity near, maybe let me use another color. Okay, let's, okay, yellow. This is yellow. Near yellow. And this equals to F minus Qn plus 1 near white. So you imagine that you have this thing. Then we can, and also let's imagine this big piece represents D. And this big piece represents FD. And this slightly smaller piece represents D0. Or not D0, but FQ D0. Then we can perturb in the following way. So we can do the following perturbation. You can define perturbation G. Let's say G equals to F here, and also equals to F here, all the way till this point. But restrict to this thing, it equals to no longer F, but F Qm H F y minus Qm. After that, you continue to use F. By using F, I mean we do not need to do perturbation. So restrict to this thing, it is still F. But then this piece will come back somewhere here. So this thing will just put F1 minus Qn plus 1 H inverse. Okay. So it is very easy to check that H is periodic just by definition. Just like you have like H here, you have like H inverse here, and all the F cancel out each other. But also, let's remember that because this sort of this thing, we have this thing. You have things like this. So this is not a proof. The proof is slightly more tricky. But let's just admit for the moment that we can do something so that by putting stronger and stronger symmetric condition, you can let these two things, two curves, be very, very close to each other. This is a green curve and a yellow, green curve and a white curve. Not only they are close to each other, and also the diffeomorphism F minus Qn plus 1, the map one to the other are close to each other, are close to identity in CR topology. This is just by this our improvements of Brenham's result. And so let us admit this for now, and also let us meet the closeness of this part can be, so there's a competition between the closeness of this part and the rotation number, but let's say this part is much, much closer than what you expect from the closeness of this thing. So basically, if you scale this twisted thing into a square, then conjugated by this map, the map is still close to identity. That's just because you can have you can assume very strong symmetric condition and use that inequality. So having this, you can know that H can be very close to identity. But if H is close to identity and FQN is close to identity, then the whole thing is close to F. And here also. Basically, here we use that you want FQN to be close to identity by our result. So basically, after you construct a G, next thing you observe is that you can have a conjugation map between G and the rotation, a rational rotation. And this conjugation, of course, has a non-bounded, uniform bounded when you putting stronger and stronger arithmetic condition on this Qn plus 2. Because you have a Qn plus 1. So all of this determined how bad this H is, or how bad you need a diffeomorphism to be to conjugate H rotation. But then you can ask for more and more, a stronger and stronger arithmetic condition on Qn plus 2. I mean, just by asking this to be much bigger and bigger. So then you can just rotate back to make the perturbation have the same rotation number. Okay, so this is basically how we do this, but I omit important thing, that is how to construct this curve, because the existence of this curve are quite known. So maybe. So basically, we're talking about how to construct this curve, gamma. So first, if you have a f, then to the rotation f, you can leave it to the universal cover. It has no fixed point or like periodic points. Then you can find you have no fixed point. Then you can find a gamma, so that the gamma is mapped to the right of gamma, something like this. But for homeomorphism, there's no reason that y, after mapping several times, it cannot be, it can intersect, it should be disjoint from the translation of this. But we can use this to show the following. If you require some strong arithmetic condition, then for instance, you have this gamma. So first of all, if you know that the gamma is CR plus 1, then let's say you have a map that takes the square, this is square, to this region, say R. Put it like this, so that the right boundary is mapped to that, left boundary mapped to this, right boundary mapped to that, and also you have some, so this is the lift of F, not F itself. So that you can also ask for this thing, HF. At least at first you put this condition only to this boundary. You can do this. Also, you can do this in a volume error preserving way using some result of I forgot his name, but Moser and another guy. And so after this, you can. So after this, you can. Okay. So basically, what I'm saying is that the C2 norm, CR norm of H can be bounded with some, in certain way, by the CR plus 1 norm of F. So this is the only place that is not explicit in our proof, because you know that for each F, you can find such curve. You can topological curve. You perturb a little bit so that it's a smooth curve. You find such thing. Of course, this construction is stable under C0 perturbation. We don't know how to do this in a very explicit way, systematic way, so that we can calculate. But in any case, this is so this is at this point is a bit hard to explain. Basically, you find certain compact sets which include all the rotation number with a bounded CR plus 1 norm, and you can do a finite number of covering. For each of these, you have some constant, and then by compactness, you have some constant. Okay, so this is the place we don't know how to make it explicit. That's why we only know generic set, but how fast they need to be approximated, we don't know. So at this point, we only construct a curve that is joined for itself. But maybe we want to know that this curve is disjoint, not only disjoint for itself, but if you iterate it Q0 times, Q0 minus 1 times, it is still disjoint for itself. So Q0 is this, the first denominator. So we can do this. Why do we can? Because so basically after Qn plus 1 time, or let's say before that, something happened. Something happened means that if you iterate it fk times, this intersected, then just by comparing the order of the point on the boundary, you know that, okay, for f q0 minus 1 time, it is still, because this order, we'll still cross that. But if you iterate another time, then it will be like this, f q0 alpha. But if you impose strong arithmetic condition, these two lines should be very close in C0. So contradiction, basically. That is how you show this. But this is only to show this disjoint is for Q0, Q0, yes. But we want to show Qn. So in this place, we need to do some constructions that so people use when they do renormalization. So basically, we consider the nth renormalized map of F. So the proof is the following. The construction is that we first get this H. We have certain bound on H. We have this. Then we can propagate this F, H to a diffeomorphism of the lift of A by using this relation. So after you lift this thing up, so we are not going to do it for F, but we are going to do it for Fn. So Fn equals to Fqn. This. So we do this for, we find a line, we find a curve here first. Let's say gamma, so that gamma is disjoint from Fn gamma. So this is parameterized by square H. So we have this, we propagate H to a diffeomorphism of that. And then observe that if you consider Fqn plus 1, then you have this thing. Because you see, like these two things commute, obviously, they commute, so that if we conjugate Fn plus 1 by H, then you know that this commute with T. So this commute with T, it means that you just consider this Fn n plus 1, but you are not going to consider this as a diffeomorphism on this A tilde. A tilde, for this Fn plus, so let's write this as a Fn plus 1 tilde. And it descends to a map on annulus to Fn plus 1 tilde, but with a minuscule f. For this, we're going to apply again what we did here. So basically, we want to improve this gamma into another gamma that has a longer disjointness property. Also, you still want to bound somehow the region between them. So basically, for this, we'll find some very twiggled curve. So it can be very twiggled. So after you map down, upward could be very bad. It doesn't even need to project to a simple curve on the disk, but we will show that it does. So let's write this Fn, gamma n. So now, okay. So basically, you see this gamma n. Gamma n is disjoint by this gamma Fn plus 1 tilde. And also, gamma n is a simple curve by conjunction, is disjoint from T. Disjoint so that you map this, you define gamma tilde by this H gamma n. So then this gamma tilde will be disjoint from Fqn plus 1 that, and also Qn plus 1, Qn. So maybe this is not a good way to write it, but if you write it on the left, you have something like this. So this disjoint from that, this disjoint from this. But you see these two things, you compare things on the boundary, you know that one thing is on the right, one thing is on the left. This is like 2. It's like 1. Basically, it looks like this. But then we can show that this is also disjoint from T gamma tilde. Because you can write this, you can, because this, let's say this is S. This is S0. You have maybe here, maybe here. Something like Qn S0 minus Qn plus 1 equals to T. So you can, so each time you apply S, you map this into the right. You apply S0 inverse, you still map to the right. So T map this to the right. It means that this is a simple curve. So this very trivial curve is actually projected onto a simple curve on the annulus. And then you need to discuss do some case by case discussion. Basically, you need to conclude from the disjointness of this thing. This is something. No, not Qn, but n plus 1 minus 1. Disjointness of this thing. You need to deduce the distribution of this sequence, not this sequence. But, I mean, disjointness of this sequence by the disjointness of that sequence. It's not difficult, but one just use this and some simple combinatorial, and you can conclude that. Okay, so this is how we show this.
Questions or comments? Let's thank the speaker once more.